Hello everyone, welcome to another section of Schneider Electric PLC training tutorials where you will learn Schneider Electric PLC programming. Okay, so for the first case, this is the exercise, and the exercise says that we should design a two input XOR gate such that the output is true only when one of the inputs is true. This is a truth table. So the output is true only when one of the inputs, okay, only if one of the inputs is true, which means that when both of them are true, or when both of them are true it is off, and when both of them are off it is off as well. And this is the ladder logic for that program. If you are to hardwire it, this is going to be the circuit for the hardwire. Okay, so this is going to be the circuit. You have two contacts, which A and B, which has been wired to input 0 and input 1, and our output is wired at input 0. Okay, so this is the XOR operation, and in this XOR operation, you know that, okay, so if we begin with the first, you see that when A is 0, when A is off, B is off, the output is off, because if A is off, A will not allow the flow of current, and this wrong will not be true. And when this branch will not be true, and when B is also off, then this branch will not be true. So A will allow, the B will prevent it. While for the first branch, A will not even allow it, even though B will allow it. In the second case now, A is off. So when A is off for the first branch and B is on, you realize that A will not allow it. B too will come in to prevent it, because it becomes now like a normally open contact like that. And for the second branch, we are still here, A is off, so A will allow it, and now B is on, so B will become something like that. So B is going to allow it also, and this wrong becomes true, and the output is on. And for the third case, A is now on, and when A is on, then A becomes like that, and B is off, so A will allow the flow of logic, B will also allow the flow of logic, and then we are going to have a logic at our output, and X becomes on. And for the last case, they are all on, and when they are on, then A becomes this. So for the last case, A is now on. If A is on, then A becomes this here, while this corresponding A address becomes this, and B is also on, so B becomes this, which is now closed, and this B becomes like this. So logic will flow from here to here and will become stuck here, so it will not reach the output, while here the logic will just be stuck at this point, and it will never reach the output, and as a result our output will always stay off. Okay, now let's see how we can simulate this in our software environment. So I'll start by configuring my outputs. I will drop my digital inputs, then I will drop my digital outputs. I will now configure them. So I have two inputs, A and B. So what does it say? Okay. Just B. Then I'll go to my outputs as well. Generate it. And I have one output, which is X. I'll just close this, then I'll create my project under programs. So I'll be giving it ladder, so I'll call it example. It's a ladder program. Okay. And I'm just going to construct it. So I will drop a normally open contact, I will drop a normally closed contact, I will drop a coil, so you can choose where to place the coil. We'll just shift it a little bit. Next, I will drop a normally closed contact, and then a normally open contact, and I will pick the horizontal line, I'll pick the vertical line. So I'll give this address A, I'll give this address B, okay, I'll give this A, and then I'll give this B. And I'll give my output X. Okay, so we have constructed a circuit. I will build the circuit, analyze the circuit first to check for bugs, then I'll build it. Then I'll put my PLC on the simulation mode. We are using a virtual PLC, and then I'll connect my PLC. My PLC is connecting. Then I will download my project to my PLC. I will run after download. Okay, my PLC is going to the run mode. So do you want to confirm run mode? Yes. Okay. So this is what I was saying. So just go back here. So the first case, they are all off, but before then, let's go to the first. I will first of all generate the animation table. So I'll take initialize animation table, and we now have an animation table here. I'll arrange my windows. I can close some of these windows, and then I'll bring this here. So I can zoom this out so that it becomes a little bit visible. Okay, so this is our animation table. We are going to go to the first case. I've already explained how to manipulate animation table in an earlier tutorial. Okay, so the first case that we want to see is that both of them are 0. So when both of them are 0, you can clearly see our output is 0, and when A is off and B is on, so A is off and B is on, so we are going to set B to on state. You see our output is 1, so this part becomes true. Okay, our output is 1, and we are going to push it back to 0. Now when B is on and A is when B is off and A is on, so I'll take A now to logic high. You can see our output is still high. Okay, so I'll send it back to 0. So our output goes to 0, and when both of them are high, so I'll push A to high, and then I'll push B to high as well. Okay, see our output goes to 0. Our output goes to the 0 state. Okay, so that is what they wanted us to implement, and we have done that. Okay, so exercise 2 says that design a 2-input XNOR gate such that the output is true if and only if both of the two inputs have the same state. Okay, so this is a truth table. Both of the input have the same state means that when they are all 0 0, the output is on, and when they are all 1 1, the output is on. And when they have, when the two input have different states, then the output is 0. That is an XNOR operation. And in this case, we are saying that if A is, for example, if A is off and B is off, so A is off, like now A is off and B is off, then this A will allow the flow of logic, B will allow the flow of logic, and X becomes on. Okay, so there is a logic 1 here which will pass through this logic. Okay, so we use it. The next operation says that A is off and B is on. So A is off, B is on. So if A is off and B is on, then B is on means this B contact becomes closed and this B contact becomes open. So in that case, A is off, so there will be no flow of logic here. A is going to prevent it from passing through from this point. And for the second branch, A will allow it, but this B is open, so this logic will be stopped here, and the output is 0. And similarly, if A is on and B is off, so in this case A is on like that and B is off. Okay, so and B is off, so if B is off, then we'll have something like that. So what happens is A becomes close, B is off, the logic will come and stay here waiting for B to get close, and A is on, and since A is on, then A becomes like that. And because A is now open, the logic will be stopped here. The logic will not go through even though B is closed, waiting for the logic to come and pass through. And finally, when they are all on, and if they are both on, then A is on, B also becomes on here, and at this point B is off also. So this branch will be the branch that will become true. So logic will flow through the first branch. Okay, so I hope that makes sense. Alright, so let's see how we can implement it on our software. Okay, so I will just have to modify this logic by replacing this with a normally open contact. He asked me, do you want to confirm modification? I say yes, and I will place a normally closed contact here also. Yes. Okay, so now we have our logic. I'm just going to build it. Accept. Okay, so it's directly on the run mode. Okay, so you can clearly see, if I go back to the animation table, you can clearly see that A and B, they are both, okay, A and B. Okay, this is from the previous logic. Let me push all of them down. Okay, so you can clearly see that A is off, B is off, which is the first case. A is off, B is off, and in that case this logic becomes true, so they are all off. Then this logic becomes true. Our output is 1. If A is now off and B is on, so B is on, A is off, the logic goes false. Okay, and when B is off and A is on, you see the logic also goes false. And finally, when both of them are on, then you see the logic goes through. So we have successfully developed the XNOR logic that will allow the flow of logic only when both inputs have the same states. Okay, so let's review what we have learned in this lesson. So congratulations, you have now understood that normally open contact is closed when the assigned bit value equals to 1 or on. Normally closed contact is closed when the assigned bit variable equals 0 or off. If there is a power flow from an output coil, then the output bit is set to 1, and if there is a power flow to an inverted output coil, then the output bit is equal to 0. Okay. All right. Okay, so this marks the end of this lesson, and please, if you have any doubt regarding the lesson, put it in the comment section below and I will review it. And if you like this video, please give it a thumb up, and if you think that there are some aspect of this video that needs improvement, please also mention it in the comment section below, and do well to share this video and subscribe so that you never miss any of our upcoming videos. Thank you very much, and see you in the next video.